Hello and welcome to exercise 5. We are looking at page 50 of the workbook here. And this is an example of an applied problem that involves the chain rule. Okay, so let's take a minute to read this problem together. So they tell us that the pressure, P in kilopascals, volume V in cubic centimeters, and temperature T in Kelvin of n moles of an ideal gas are related by the formula PV equals nRT. Okay, and those of you chemists out there might recognize that as being the ideal gas law that we're looking at. Okay, and then they go on to just note that the R is representing a constant of proportionality here. And then the next sentence, they start to give us some information about the specific values of these variables. So let's suppose that we have a sample container that contains 100 cubic centimeters of 0.002 moles of a gas. Okay, they give us a room temperature of 300 Kelvin, and then they give us some information about things that are changing. So if this sample is compressed at a rate of 2 cubic centimeters per minute and heated at a rate of 1 Kelvin per minute, how fast is the pressure of the gas changing? Okay, so there's a lot involved in this problem here. So as we start to pick through it, let's first maybe notice what they're asking us. Okay, they're asking us how fast the pressure is changing. Okay, so it might be practical to start with the formula that they gave us and to solve that equation for P, since it's the derivative of P that we're after. So I'm going to take this equation and divide both sides by V. Okay, that's going to give us just a P over here, and we can either divide by V or multiply by V to the minus 1. So I'm going to write it as nRT times V to the negative 1. Okay, and then I'm going to draw a dependence diagram. This is going to be a chain rule problem, so it's always helpful to have something like that. So it's pressure that we're trying to take the derivative of. And what variables is pressure a function of? Well, we can kind of see that here. There are some constants like N and R in there, but the two variables are temperature and volume. Okay, so P is a function of temperature and volume. And what are temperature and volume a function of? Okay, well, notice they're giving us information about rates of change with respect to time, minutes. And so actually those two variables are functions of T, time, in this problem. Okay, so there's kind of our visual setup. And in an applied problem, I always like to start out by trying to take note of what it is that we're given, what might help us, and then where we're headed. All right, so let's take a minute just to write down what we're given here. Okay, and I'm looking kind of at the last sentence up here. So one thing they tell us is that the gas is compressed at a rate of 2 cubic centimeters per minute. Notice that that's a rate of change of volume that they're giving us. Okay, so dV dt, the rate at which volume changes, is negative 2 because it's being compressed. That's a negative rate of change. Okay, and then another piece of information is this. It's being heated at a rate of 1 Kelvin per minute. Okay, that's a rate of change of temperature, and it's positive in this case. Okay, so we know those two things. And what is it that we're being asked to find here? Well, we noticed that already kind of in the last part of the statement. We want to know how fast the pressure is changing. Mathematically, we can write that as dP dt. Okay, and then we might note that we're being asked to find that pressure change at under specific assumptions, in particular when the volume of our sample is 100 cubic centimeters, the number of moles is 0.002, and the temperature is 300 Kelvin. Okay, so there's our setup. And next thing to do is to write down a formula for dP dt. We can use our diagram to help us because, as usual with the chain rule, it's a matter of asking how many different paths are there from P to T. Okay, and there are two in our case. Here's one of them. So the first path takes us from P to T and from capital T to little t. So if we write down those derivatives, we're going to get the derivative of pressure with respect to temperature times the derivative of temperature with respect to time. Okay, and then we've got another path that takes us from pressure to time. And it goes from P to V and V to T. So in terms of derivatives, that's going to be partial P partial V times dV dt. Okay, there's our chain rule formula. And we're ready to actually take these derivatives now. Okay, so the first thing that we need to calculate is partial P partial T. So let's find our formula for P. That's sitting up here. We want to take the derivative of that with respect to the variable T. If we do that, the derivative of the T that you see there is going to turn into a 1, and the other pieces are just going to come along for the ride. So we're just going to get nRV to the negative 1 out of that. Okay, and then we have dt dt. Okay, we'll just rewrite that. Now, partial P partial V, okay, same deal. We're going to go back up to our formula for P. This time, we're going to take the derivative with respect to V. So that would mean taking the derivative of this V to the negative 1 term. Using the power rule, that's going to turn into negative V to the negative 2, and it's going to give us negative nRT V to the negative 2. Okay, and finally, times the dV dt that's at the end here. Okay, and at this point, we're ready to start substituting things in. We're hoping to get a number out of all of this. Just to make it easier to substitute stuff in, notice that there's an nr in all of these terms. So I'm going to do one algebraic step before we start substituting numbers in. I'm going to factor that nr out. Okay, and if you do that, factor it out of both of these terms, you're going to get this. Okay, now let's go ahead and substitute our values in. So let's see, we've got n from up here, n is 0.002. Okay, we've got r next, and let's see, I have to sneak a peek at that. That was 8.314 times 10 to the third. Okay, there's our n and our r. Okay, and then in the parentheses, next thing we come to is v to the negative 1, so that's 100 to the negative 1. Okay, and then what about this dt dt? Do we know what that is? Okay, notice that we do. That was part of the given piece of information that we wrote down at the beginning. Okay, the rate of change of volume is negative 2, so we can fill that in as well. Okay, continuing. Then we come to TV to the negative 2, so T is, oh, not 100, sorry, 300. Okay, let's fix that. So T is 300, V is 100. Okay, and then finally we come to dV dt, which we can see. Oh, hang on just a second. I noticed that I made a mistake here. Back up. Maybe you probably already noticed this. Okay, back up for a minute to this term. Okay, dt dt, that's actually this number 1. I think I mistakenly wrote negative 2 there, so let's fix that. Okay, that should actually be one. Okay, there we go. Okay, and then when we come over here to dV dt, that was the number that was negative 2. Okay. All right, and just taking a quick glance, I think we've got the numbers in the right place now. Yep, looks like we do. Okay, and at this point, it is a matter of just kind of going to your calculator and seeing what you get out of all of this. Okay, so I'll let you double check me on this, but what you come up with is an answer of 1.164. Okay, that's the rate of change of pressure with respect to time. What should the units on that answer be? Okay, well, just ask yourself, what were the units that we were measuring pressure and time in? And pressure was being measured in kilopascals, and time was being measured in minutes. Okay, so we have just demonstrated that the pressure is increasing at a rate of 1.164 kilopascals per minute. Okay, actually minute, not minutes.